Good morning, students. Today we will start a new topic. We will see another energy generation process which is different from solar energy generation process, and that is thermoelectric energy generation and materials which are being used for thermoelectric energy generation. So if we look at previous topic, that is photovoltaic energy or the solar energy, what we have seen that over the time people have actually fabricated different solar cells, starting from silicon solar cell, crystalline silicon solar cell, amorphous silicon solar cell, and then thin film solar cell, and followed by dye sensitized solar cell, quantum dot sensitized solar cell, perovskite sensitized solar cell, and finally what we have seen, people are also trying to make multi-junction solar cell, combining different solar cells to achieve better efficiency. So this is of course one very good approach, and we see everywhere that there are a lot of work is going on in solar cell, both in terms of research and also in technology. However, there are some problems involved in solar cell which we have discussed when I was discussing various solar cells. One obvious problem is that we always don't get very bright sunlight, and it also differs from one geographical location to another geographical location. Some places people even do not see sunlight for months together. So that means if somebody is to use photovoltaic cells as a energy generation process, then one is to store also that energy. So another the technology is involved, because almost say 3-4 months there is no sunlight, so one cannot get direct energy from sunlight, but one is to store that. That actually involves another level of cost. So this is a real problem with solar energy. And another, as we have discussed, that although there are a lot of approaches made by different scientists, different engineers, but still people are not at a stage to achieve very high efficiency of solar cell. So there is always a search for different energy resources. And one very simple but very efficient way of generation of energy is to convert heat energy to electrical energy. Now, when I want to say heat energy to electrical energy, I mean it is not heat energy, it is waste heat energy to electrical energy. You will wonder that how much heat is being wasted every day across the globe. If you just consider USA, almost around several thousand terawatt of energy, heat energy is being lost or wasted because of their automobiles and vehicles. Nobody is using that energy. On the other side, when we talk about energy consumption and energy sources, we focus on the petroleum product, but we all know that there is not only a scarcity of the petroleum product but also very high price. So therefore, the heat energy which are being wasted every day in different forms should be used in electrical energy or any form of other energy, and here we are more concerned about electrical energy. So if it can be done, then we have plenty of source of energy which are of zero cost because it is wastage and you are using this for generation of electrical energy. So how it is? So look at this waste state of electricity. So this is actually a pie chart of waste state of electricity. So you can see that 66% energy is lost as waste heat. Okay. And what are the sources of this waste heat? It is automobile. This is nuclear power plant. This could be thermal power plant, different factories, and different other sources of heat which are regularly being lost and that they are not being used. But can we just get this energy back for some useful purpose? That is for generation of electricity. So the idea is that can we convert heat energy to electrical energy? And the idea is not very new. More than 200 years back, Seebeck gave an idea that if there is a difference of temperature in a thermocouple. Thermocouple is basically a device where two metallic wires are connected and two contacts are made. But if there is different temperature, due to this temperature difference, there will be a production of voltage, electrical voltage. So it is nothing but creation of electrical energy from temperature difference, that is from heat energy. And then now again people look at this particular process which Seebeck had given long back, and they try to understand that so much amount of heat is being wasted. Can we get back those heat in terms of electrical energy, and can Seebeck effect play a role? And that is where these thermoelectrics play a role. So all this heat energy, waste energy, if you would like to use as electrical energy, then there is something which come in between is called thermoelectrics, which was discovered long back by Seebeck. So the first we will look at what was the fundamentals of thermoelectrics, what Seebeck had given, and after that Peltier had just extended that thermoelectric effect. And then we will see that how one can make a thermoelectric generator, okay, for production of electric power and electric energy. All right, so let us first see what are thermoelectric effects. So as I mentioned, which Seebeck discovered long back, that if there are two dissimilar metals, you make it in wire form and connect them, make two contacts and make two junctions basically, and create a temperature difference. So what essentially you have to do, that you have one metal, then you have another metal, you make this junction, okay. So suppose the red one is the metal A and the blue one is metal B, and I have a hot junction with temperature TH and a cold junction with temperature TC. So what essentially I have created a temperature difference which is delta T is equal to TH minus TC, okay. This is very simple. You can take an ice bath, and keep this junction here, the ice bath. Okay, and here you keep it at room temperature. You can also heat it little bit or keep it at room temperature. So there is a temperature variation. So very simple, you can do it in the lab. But if you connect a voltage source, voltmeter here, you will see there will be a deflection in the voltmeter. That means this temperature difference which is being created in this junction of two different metals have actually converted to electrical energy in terms of voltage. This is what Seebeck has given long back. And then after that, people have used this particular concept, particularly in temperature sensors. If you go to laboratory, you will find people use this thermoelectric based temperature sensor. This senses temperature using the Seebeck effect, and there was for a long time this particular application was used. Okay, so this is one effect which is known as Seebeck effect. So this is the first thermoelectric effect. Okay, so there is another which was proposed by Peltier. What Peltier proposed, that you just make the reverse situation. That means you don't keep temperature difference, you pass a current through this particular contact. Okay, so again you have a red metal wire and you have a blue metal wire, and now you pass a current from a voltage source in this. So this is one junction, this is another. So what will happen in this case? The heat will be lost at this point. Okay, so I just connect them this. Heat will be lost in one junction and heat will evolve in another junction. So what okay, so that means now I have created a temperature difference Tc Th, that means now I have created a temperature difference of Th minus Tc just by passing current in this thermocouple. Okay, and this is known as Peltier effect. And this Peltier effect was used and also used these days also in the refrigeration. Okay, there is another application which you can study. So these are primarily two thermoelectric effects. Okay, there is another effect also, thermoelectric effect, that is the effect where if you have a conductor and then you create a temperature gradient along the conductor, then you can see a flow of current. This also is also included in the thermoelectric effect. This was discovered by Johnson. Okay, so these are the three thermoelectric effects. But when we talk about thermoelectric generator, which is the primary focus of this particular topic, we will see that basically Seebeck effect is used in thermoelectric generator. So let us try to understand why it happens, why there is a temperature difference can give rise to some kind of electrical potential. So let us look at this particular diagram. So now I have these two junctions which are one at T plus delta T, another is at a temperature T. Okay. So what temperature difference I have created is delta T. So if I try to understand it, because there are two metals, so if you look at in a metal, the electron is distributed as per Fermi-Dirac statistics, that you know free electron theory of metal. If you study, that electron is basically distributed as per Fermi-Dirac statistics. So what happened when you look at the occupancy of electron in a metal? Suppose this is F, and look at the distribution of electron, and this is electron energy. Okay. Then at 0 Kelvin, absolute 0, the distribution of the electron is like this. We all know that. And this is an energy which is known as Fermi energy. Okay. So this is at 0 Kelvin. Now what happened? Now you look at, I have this particular junction which is at a temperature T plus delta T. It is the hot junction. Okay. So I have increased the temperature of this junction. So what will happen? The electron, they will now change their distribution. Okay. And this distribution will go beyond the Fermi energy along y-axis, something like this. Okay. And along x-axis also. So there are now density of states which will appear beyond the Fermi energy, because you are raising the temperature, and therefore that will be much sharper in case of the metal or the junction where temperature is higher. It is true that here also the electron density of state will go beyond Fermi energy, but as this particular junction is at, you know, is at low temperature, but that is not that sharp. The variation of electron density of state is not that much. So that means there is a concentration gradient of electron from this to this. So now I draw it in a simple way. I just consider a bar. Okay. This is a temperature T plus delta T. This is a temperature T. So I call this is hot, this is cold, and here I have in hot side we have more electron density of state. Okay. And then what will happen? It will try to, that means the concentration of electron is higher. So therefore it will try to flow towards the cold end. Eventually the number of electrons which will go towards the cold end will increase, because it will follow that, you know, this concentration gradient. Now this cold end will become, you know, negatively charged disorder, because it is electron rich, and equivalent positively charge will be developed across the hot side. So now what you see, that slowly in the equilibrium it will be balanced, and this actually will create an EMF V. This is the very simple way to explain why the temperature difference can create a voltage, or a very simple way to explain the Seebeck effect. Okay, so that means the voltage which is being generated is basically proportional to temperature difference. Okay, so if again I look at this particular circuit, this is a sort of thermoelectric circuit, and then you look at, this is the cold side now, this is hot side, the green one is metal A and this is metal B, and we have a potential difference created here because of the temperature difference in hot and cold side. Okay. So what I mentioned is that the potential generated here is basically proportional to delta T, and if we write it equal, then I have to multiply with another factor which is known as popularly Seebeck coefficient. So, S is Seebeck coefficient. In the literature you will find that people also represent Seebeck coefficient S or alpha. This is basically delta V by delta T. Okay. So this is a very important, the equation which one should look at when one start with the fundamental understanding of Seebeck effect or thermoelectric effect. So this is the one formula which we should know, and the second is the voltage which is being generated because of temperature difference is actually, there is a variation with the temperature, and the variation is actually given by this particular equation, C plus AT plus BT square. So it is sort of parabolic variation. So if I just look at this variation, which follows this equation, then it will be something like, if it is temperature, this is basically the temperature difference between the two junction, and if this is the voltage, then this parabolic. Okay. So one can find out this particular temperature Tn by differentiating this with respect to temperature. So this is A plus 2 Bt. So if you write dB by dt is equal to 0, then this becomes A plus 2 Bt. So T is minus A by 2B. T is equal to Tn. Okay. So this is a very simple, the mathematical equations which describe Seebeck effect. So we should always remember that how much voltage we generate, it depends on how much Seebeck coefficient of a particular thermocouple is. Therefore, Seebeck coefficient plays a very important role. Okay. So these are all background of the Seebeck effect or thermoelectric effect, and now our idea is essentially to understand how this thermoelectric effect or Seebeck effect is useful in thermoelectric generation or our thermoelectric generator. So thermoelectric generator is nothing but a simple thermocouple kind of configuration only. Okay. But the material aspect of a thermoelectric generator is extremely important. When Seebeck worked with the thermoelectric effect, he was just using two metals, and after that people have made lot of thermoelectric sensors, they are using two standard metal. Okay. and all the values of the Seebeck coefficients are there. You can find it in the literature, okay, or in the standard table, all the values of Seebeck coefficient of different metal and different metal combination for different thermocouple. However, when we want to make a thermoelectric generator, what we have to essentially know? The most important factor that is used in thermoelectric generation process is known as figure of merit. So let me first define the figure of merit. Figure of merit Z is defined as by this equation. Okay, let me write this is equation 3. So what this equation tells? That there is some quantity which is known as figure of merit for thermoelectric generator, which is defined by Seebeck coefficient square into thermal conductivity divided into electrical conductivity and divided by thermal conductivity. Now the question is, why this figure of merit is important? So how to get this particular the figure of merit formula? I will come back to this point little later. We will mathematically derive and show that how figure of merit comes into thermoelectric generator. But let us just take it from the literature at this moment, that there is something called figure of merit which is important for thermoelectric generator. So that means if I make a thermoelectric generator TEG, then we should have high Z, that means high figure of merit. So if you have to make a high figure of merit, we have to choose material also accordingly. And you will see later when I will discuss the mathematics that figure of merit actually is directly proportional to the efficiency of a thermoelectric generator. If you have higher figure of merit, then there is a higher efficiency of a thermoelectric generator, higher power output. Okay. So that means if I want to make an efficient thermoelectric generator or thermoelectric device, I should have a high Z or high figure of merit. So now the question is, if we go back to our old thermocouple, okay, where two metals junctions are formed, are they okay to make a thermoelectric generator? Can we get very high figure of merit from two metallic junctions? Let us look at this issue. So our idea is that we have to make a high figure of merit thermoelectric generator. Now, if you look at the theory of Seebeck effect or Seebeck coefficient little more in the free electron model, you will find that Seebeck coefficient actually is proportional to, inversely proportional to the charge carrier density N, that means electron, okay, in case of metal. So that means if charge carrier density is high, then Seebeck coefficient is low, and if charge carrier density is low, Seebeck coefficient is high. That means if we consider a metal where charge carrier density is much higher, Seebeck coefficient will be lower. Okay. So now let me just compare this metal, semiconductor and insulator. So what I am trying to do is say the metal, insulator and semiconductor. Okay. So first is the Seebeck coefficient, because if we look at the figure of merit, It depends on Seebeck coefficient square sigma by kappa, where sigma is electrical conductivity and kappa is thermal conductivity. So, what happens, so that we can understand the Seebeck coefficient is low in case of metal because of high charge carrier density. For insulator it is high, okay, because of relatively lower charge carrier density, and for semiconductor is also high. Now come to electrical conductivity. For metal it is very high, okay. For insulator it is very low, and for semiconductor it is, you can say, it is intermediate, so it is relatively lower. Sorry, it is relatively, I should write it, relatively higher, as it is higher as compared to, you know, insulator, and it is lower as compared to metal. Okay. So, now I come to the third quantity, that means thermal conductivity. Thermal conductivity is high in case of metal. In case of insulator, thermal conductivity is low, and in case of semiconductor it is relatively lower. Okay. So, now let us look at the merit of all these three materials. So, as in the metal the Seebeck coefficient is quite low, Seebeck coefficient should be high. If we have to get a higher figure of merit, Seebeck coefficient should be high, that is what we have seen. But if Seebeck coefficient is low, that means we cannot get a very high figure of merit for metal. So, let me disqualify this. Now, insulator, what happened? Although in insulator Seebeck coefficient is high, but the electrical conductivity is so low that it makes entire figure of merit low. Okay. Therefore, insulator is also disqualified. And now, if we look at semiconductor, here Seebeck coefficient is, these are all intermediate values, you can say. Seebeck coefficient is higher as compared to metal, lower as compared to insulator. So, this is good that we have an intermediate value. As far as electrical conductivity is concerned, for semiconductor, electrical conductivity is higher as compared to insulator. So, not that low as insulator. And also, if we dope semiconductor, that is what we will discuss later, how to design an insulator material for thermoelectric generator. So, if we dope semiconductor, we can even increase the electrical conductivity. And now coming to thermal conductivity, this is relatively lower. Thermal conductivity, as per this equation, should be low enough. Okay. So, the thermal conductivity is lower here, and thermal conductivity is low for insulator, and thermal conductivity is high in metal. Okay. So, metal and insulator already are disqualified because of this, but semiconductor, let us, we give it a green mark. Okay. So, this means that when we want to design a thermoelectric generator, we have to choose a material which are semiconducting in nature. Okay. So, rest of the, the research and development which are done in thermoelectric material, all are based on semiconductors, and that is what we will discuss as we progress in this particular topic. And you will see how many semiconducting materials people have used. There are some other materials also recently people have proposed, that also we will see later. Okay. So, if we look this particular aspect little more, carefully, and look at how this particular, all these three physical the quantities are varying for metal, insulator and semiconductor, and plot them. So you can see this is insulator. So this is the kappa, the thermal conductivity, this is Seebeck coefficient. So if you look at insulator, you see the Seebeck coefficient is quite high, okay, and then it falls. When you come to semiconductor, it is decreased. When you come to metal, it is drastically it has decreased. Okay. So now look at sigma, that is the electrical conductivity. For insulator it is very low, for semiconductor it is intermediate, this is the region for semiconductor, okay, and then for metal it is high. Okay. Now you look at the thermal conductivity kappa. This actually thermal conductivity, as we know from the free electron theory of metal, it consists of two component. One is electronic thermal conductivity plus lattice thermal conductivity. So we will come to this point little later. So what happened? The thermal conductivity in case of metal is high, you can see, and the thermal conductivity in case of insulator is low. Again, from semiconductor it is intermediate. So this particular plot actually defines very nicely that semiconductors are the material for thermoelectric generator. Here it is actually not figure of merit, this is called power factor. Power factor is basically defined by S square sigma. Okay. Where figure of merit you just divide by the thermal conductivity. Okay. So what we can see that the power factor actually maximizes in case of semiconductor when we plot with respect to logarithm of the charge carrier density. Okay. So what essentially we have seen here, that the first thing is that the temperature difference can create a EMF. Okay. And the second thing is that how this EMF varies with temperature, okay, or the temperature difference. And then we have seen, which is more important for thermoelectric generator, those we will discuss little later. And this thermoelectric generator, the efficiency and power of the generator depends on a quantity which is known as figure of merit, that is what we have discussed. And then another quantity which is also useful in this is power factor. Okay. So now whatever we will discuss the thermoelectricity in terms of semiconductor. Okay. So far whatever thermocouple we have made, or whatever we have discussed, or what Seebeck made, and then people are using this configuration which are are going on for several years, are now being changed when we consider the semiconductor. So in the semiconductor, if you look at what happened, so this is, there is a heat source and this is an heat sink. Okay. So in the semiconductor, basically the electrons flow from hot junction to cold junction. So hot end to cold end. So suppose I have N-type semiconductor and I have N-type semiconductor and I have P-type semiconductor, then electron starts flowing from N-type to P-type. Okay. And then it is exactly same as I have discussed earlier, that when there is a variation in the temperature, or there is a difference in the temperature of the two junctions or the two semiconductors, there is a potential difference created because of flow of electron from one semiconductor to another semiconductor. Okay. So this is a way one can realize thermoelectric effect in semiconductor. And now what I just like to show you that how a small thermoelectric generator module is being made. So you can just look at, so this is a small thermoelectric generator module, where this is a P-type semiconductor and this is an N-type semiconductor. Okay. So this is a temperature Tc, which is a cold junction, and there is another temperature Th. So that means this is connected with a heat source. Okay. and there is a heat sink here, all right, and the temperature difference is being created. And that's all. That is all the module is. What you do after that, because of this temperature difference, a potential difference is created, as I have discussed earlier, and because of that there is a flow of current that can be flown across a load resistance. Okay, and then you generate the power. So that is all the starting point of a thermoelectric generator module. And in future we will see how to analyze this thermoelectric generator module, how to get the efficiency, how to get the power, how to maximize this efficiency, power, etc. But before we go to all these, the design and device aspect as well as material aspect, let us look at what are the advantages of this entire the thermoelectric generator device. What are the advantages? The first advantage is that it is completely a solid state device. It's a solid state construction, so there is no moving part, there is no vibration issue. Second, it is available for 24 hours. Sunlight, you are not sure. In photovoltaic device, the source of energy, which is sunlight, may not be available for the entire day, may not be available for many days, but this is always available. Wherever there is a waste heat, there is a thermoelectric generator. What I mean, suppose you are driving a car and the heat is being wasted, you just plug in a small thermoelectric generator device, it will take up this temperature difference and it will work. It will keep on giving power and energy to some sort of devices which are connected in, which are there in your vehicle. So therefore, it is 24 hours a day, and there is hardly any noise. Okay. In fact, there is no noise and the maintenance is very low. It is very convenient power supply, and it is a stabilized temperature of devices. Okay. There is hardly any fluctuation which we generally see in many of the electrical energy sources. And then in any environment you consider, there is no change. It is always having a very good lifetime of operation. So the temporal stability is always very high, because there is nothing which can deteriorate it unless and until the materials which are being chosen for thermoelectric generator are being deteriorated in certain environment. And there are a lot of space and military application, we will see later, and this is really very important, because if you can consider that if there is a spacecraft which is going high, I mean in the outer atmosphere, and then you have to power small devices in the spacecraft. Okay, you need some sort of small energy generator, and thermoelectric generator does this job very efficiently. Okay, similarly these thermoelectric generators you can see people have used in the military application like in tank, etc. Okay, the performance is scalable and it is simply waste heat to electricity. Okay, and then another very important thing is that when I make an energy, the source or energy device, we have to always consider that how much space it is taking. You see, if you make a big battery, it takes a very huge space. It is very bulky also. The batteries which are being used, suppose an inverter, which is an alternate source of energy at your home, they are very bulky. You cannot lift it. Okay, but if you have a small thermoelectric generator, you can even lift this device. Okay, so that is very important, and it is very much portable, and it is having much less weight as compared to battery. Okay, which is a household power supply. So when we have so many advantages for a particular electrical generator, it is really important that we look at it very carefully, do enough research to get it a highly efficient energy generator or power generator. And these are the motivation of our next lectures. Thank you.